ready to start, and we have about 5 minutes. Here's our picture of the surface bounding A, and B is piercing the surface once, like that, right? But the A could easily have bounded some other surface entirely. So we might consider an A, a little curve like that, but maybe it's the boundary of some much more complicated surface out here like this, right? And it's also the boundary of this little simple surface over here, right? So here's S1, and here's S2, and here's A, Y-oriented. So we're practicing a little bit. The A, I thought I'd put the A in the same framework as I had before, and then think about that. So here's the A, and it's bounding a little disk here. And on the other hand, it's bounding this surface here. And by the way, when you think about that, let's just draw another example. Then I put an orienter on the surface itself in the form of a little curve that goes around. So I think of that as producing a positive normal to the surface. And I put it in parallel to this. So that means it's going to go around. Notice it goes around in the opposite direction, seemingly, when I do it over here, in order for it to turn in parallel to this, right? If I put it that way, well, then this would have the wrong normal, right? So I don't like that. If I want the surface to have the same normal, I should put these orienters in the same, as though there was no belt around the surface, and you just move the orienter up and down to show you where the positive normal was. But then you see that this one goes against the orientation of the curve, and this one goes with the orientation of the curve, and that makes sense because that is canceling, right? So it's just our convention about how normals are behaving with respect to the boundary. And so if we have this curve alpha, which is on the boundary, I called it A before, then I have that the boundary of S2 is equal to minus alpha by my convention, right? Going in the wrong. I take my boundary with regard to the surface and I'm getting minus alpha. I'm going in the opposite direction. I have the boundary of S1 is equal to alpha. And so if I can think algebraically, S1 plus S2, the boundary of that is going to be equal to 0 by my algebraic convention about canceling boundary if they go in the opposite direction. So this is the natural way to think about adding things together algebraically so that when you have boundaries between them, you might want them to cancel. And you've probably seen, I'm just making some remarks here, and you've probably seen this before, for example, in advanced calculus, if you hadn't seen it in some topological situation. Suppose I have 4 bits of surface here like this. They're all oriented to have a normal, which is pointing out a board, right? And then you see what happened on the boundary, and the boundary, let's do it in a different color. Yeah. So the boundary is going like this, just following the directional indication of that thing. So that's the way the boundary goes. And this one, well, you see the boundary goes oppositely along the shared part. So when the bits of surface are set so that they all have the same positive normal, then all of the, oh, I'm in mistake here. This one, yeah. Always think. Let's see how my drawing. I'll do this one in brown, so I don't have to color. Let's see if we got it right this time on the top before I start drawing on the bottom. This is going in the same direction as my orienter. This one is, and now this one will. This one. And all the shared boundaries cancel, right? They all just gone, and you're left with the boundary of, if you call this X, Y, E, and W, and by the same algebraic convention, the boundary of X plus Y plus C plus W is equal to gamma, where gamma is this curve that goes all the way around the outer boundary, right? So that you see that you have a nice algebraic image, which you probably learned when you were integrating surfaces, if you didn't learn it in the other place, right? Integrating on surfaces. You have a nice algebraic way in which things with boundary can fit together and their boundaries can cancel, and so you get the larger boundary out of the whole thing. And we're getting the boundary of this amalgamated object out of the boundaries of its individual pieces. And so we can algebraically think about boundaries in a form such that the boundary of X plus Y for arbitrary X, Y are equal to the boundary of X plus the boundary of Y. We can think that way, right? So then that's the setup in which I'm thinking about this. And then we're thinking about how another curve, like this curve, might be coming along, and then it pierces the upper surface, and comes on down through here, and then it pierces the lower surface and comes back out, right? I'm staying with one color. I'm sorry about that, but it's so awkward to keep changing colors. So then you see this, and I wanted it to be, floating above, piercing the surface as it came in, and then it goes inside, and then it comes back outside, maybe in the back. But then if you check, how is this piercing with regard to the orientation of the surface, you'll see that that the total sum of the intersection numbers is equal to 0, right? If you're going to have to look and make the drawing yourself, looking at the orienters on the surface, and see that the total intersection number is 0. But we've seen it before, like if you had a surface here and you had a curve that came down through, and then it came back up through, and continued on up like this one. Like this one. Let's say this goes up and the orientation on the surface is this way. So that's a positive intersection with this surface, and then it comes back down through, but then of course that's a negative intersection with the surface. The same calculation is going to show you that if you had a closed surface and you watch what happens, then you will see that that the total sum of the intersection numbers is 0. And that's basically the reason why it doesn't. That's the first level geometric reason why it didn't matter which surface you chose, because you will find that the total intersection number is 0, which means that the sum of these intersections and these intersections are giving the same linking number. Now, why is it zero? Well, the reason it's zero, as I said, is essentially because the surface in 3 space bounds a 3-dimensional object. But I think I'd better not try to go into any more details of that right here. But if you want to think about, if you want to read something about intersection numbers, I'll look around and see if I can find something further for you to read about intersection. There is a further thing that's worth mentioning in regard to this. My suggestion, as I said, is that you look at various examples before you try to make a proof. And so, you know, this is an indication of the direction for some examples. But let's see, why don't we erase this part of the board? I want to give you a lower, what I want to say. This is yet another picture about linking numbers, which is going to sound a little more abstract, but it's worth thinking about. Here you are in 3 space, which I'm drawing as a line, and then think of above that 3 space is positive 4 space. Okay, so positive 4 space is equal to the set of x, y, z, and t, such that x, y, and z are real numbers. That's 3 space. And t is in the real numbers, and t is greater than or equal to 0. So that's upper 4 space like that. Okay. And then I say that you can examine 2 curves in 3 space, and you can do the following strange thing. You can find some surface whose boundary is 1 curve in upper 4 space, and another surface that bounds the other curve in upper 4 space, and these 2 surfaces will intersect in some points. So you have a surface FA and another surface FB for the curves A and B, and A and B are sitting inside of R3, and FA and FB are surfaces that are sitting inside of R4 plus upper 4 space. And we look and transverse to one another in general position as nearly away from one another as we can make them. And then we take the linking number of A with B is equal to the intersection number of the 2 surfaces in 4 space. So you have to try to imagine that and see if any of this makes any sense to you, but we'll do an example or 2 and then you'll see that it does make some sense. First of all, you have to understand that it really may be the case that if you, and I'll show you an example so you see it, that you could have these two curves which are linking each other once. And if you try to produce some disks in 4 space, you will see that I can give you 2 disks in 4 space, and those 2 disks intersect in 1 point. And they do it just like this. Let's look at a low-dimensional version. Here's 2 points in the real line. And here's the upper real line, upper two space, okay? Upper two space above the real line. And here's two other points there. So this one is B. And this one is A. And A bounds on an interval up in upper two space. And B bounds an interval in upper two space. And the two intervals are intersecting in one point right up there. And that's the linking number of these 2 points with these 2 points. A pair of points in the plane, in the line, excuse me, a pair of points in the line can be linked with another pair of points in the line if they have their feet, if the 2 points are in between one another, as I've drawn them. If I have these 2 points and these 2 points, then I will say that this pair is linked with that pair. Whereas if I have these 2 points and these 2 points, I would say that they're unlinked. This is the lowest dimensional example of linking that I know, right? And it's often the case that the lowest dimensional case will still give you an indication of the logic of the situation. And when you are looking at the linking of pairs of points, then you see clearly, a pair of points, it can bound an interval. The other pair of points can bound an interval. And the fact that these are linked with one another has to do with the fact that these two intervals in the upper space have to intersect with one another, and they intersect in one point. And that one point is the linking number of these two. And furthermore, you see that that's not dissimilar to looking at the intersection number of something that bounds A with B, because down here in the real line, here's somebody, this little interval in there that I drew, that bounds A. Boundary of this is A, and there's the intersection point of B with A, the 1 point. And when you deform that interval up into 4 space, you still see the intersection number. Okay, so what I'm saying is that phenomenon goes up dimensionally this way, like that. But as long as we're thinking about it, let's think about it a little more carefully and see that this really can happen. In other words, I'm claiming that these two links, the Hopf link, this link, linking number 1 link, each of them bounds a disk in upper 4 space, and the disks intersect each other once. How could two surfaces intersect each other once? And abstractly, you won't have any trouble with it at all. Let's look at 4 space, right? 4 space is equal to the set of all x, y, z, and t. So, I want the following: 2 planes that intersect in 1 point, like 2 lines intersecting in 1 point in R2. This we're familiar with. 2 lines can intersect in 1 point in R2, like that. And if you move 1 line, you see, I'm thinking topologically, so maybe one of these lines becomes wavy and the other one becomes wavy, but there just isn't any way for me to get rid of the intersection point that way. And I'm thinking of moving them around so that they still intersect each other with different tangent vectors, so I don't worry about them becoming tangent to one another. But even if they did become tangent to one another, you see that I'm not getting rid of the intersection point. It might do bad. And then the tangent to this one would be equal to the tangent to that one. That could happen, but I'm not getting rid of the fact that they intersect if I move them around. They're differentiable curves, so they have tangents, and I'm assuming they have non-zero tangents. And then if I move them, I say that they're transversal to one another if the tangent directions are different. So then I have a nice crosswise intersection like that. I can't get rid of it. Well, what is the analog up one dimension? Is there an analog up one dimension into four space rather than, well, how would you think of this? This is, here's R2. And this line here is the set of X comma 0, right? And this vertical line is the set of 0 comma Y. And these two sets only intersect in 0, 0. So, see, you know how to say it, and you see that the logic of that will go up a dimension. So I can, if I want to, in my four space, I can take one plane to be equal to the set of things of the form 0, Y, T. Oh, I wanted two planes, excuse me. So I'll take this plane. So I'm going to take X, going to take X, Y, 0, 0. That's a nice plane. And my other plane is going to be the set of things that form 0, 0, Z, D in my four space, right? And this is a plane. And this is a plane. And the intersection of P and Q is exactly equal to the origin point. 0, 0, 0, 0, right? They intersect that way, and they intersect in exactly analogous way to the way these two are intersecting, like that. The next point, I didn't think about how I wasn't intending to do this. So now my claim is that if I were to do this right, then I would show you that this and this also have exactly that property that you can think of them as taking these two planes out there in space and having a circling one and a circling the other that are intersecting. But in order to do that, the way I just told you about it is not quite the way I wanted to say it, because I said, here is R3, and then above it is R4 plus, right? And then I'm saying it is true that you can put a disk in here and another disk in here, and those two disks will intersect in one point. But since I described these two planes this way, I need to reconfigure the way I'm going to describe this. So rather than go further with this, I will leave it for you to think about, okay? It's quite clear to you that, that these are two planes that intersect in a point. And how, but let's consider also, how could we get a three space that would be related to them? So let's go down a dimension and see that. It's a different three space than the one I had in mind, that's all. Here in the lower dimension of R2, I have two lines that are intersecting in a point. Now, what if in R2 I considered the circle? a circle is equal to the set of xy such that x squared plus y squared is equal to 1. And now, within that circle is equal to the boundary of the two-dimensional disk, and that disk is equal to the set of x and y such that x squared plus y squared is less than or equal to 1. Okay, there's the disk right in there. And you see the two lines that are intersecting. And out here in the circle, you see a link in one dimension. Here are 2 points, and here are 2 other points, right? And now you have the star is going to be A, and the dot is going to be B, and the absolute value, since we aren't orienting things, so the linking number between A and B is equal to 1, and it's reflected by these 2 intervals that are intersecting there, right? That's clear, it's working, right? That's fine. But now you see what I can do dimensionally. I can say, oh, why don't I look at the 3-sphere as the set of x, y, b, t, such that x squared plus y squared plus c squared plus t squared is equal to 1, right? There's the unit 3-sphere sitting out at the origin, one unit away from the origin in 4 space, right? So putting down one equation cuts the dimension of it down by 1, and I have the 3-sphere sitting in 4 space like that. Then I can think, if I want to, of upper 4 space as interior 4 space instead. Another way of thinking about I have 4 space, a half space. The half space here that we're looking at is the interior disk, and there is the exterior disk. So I can think of the 3-sphere as sitting in 4 space like that. And I have this plane, and I have this other plane. And so I should think about what is the plane, my plane P, intersected with the 3-sphere. And let's find out what it is, okay? By writing down the algebra and letting it tell us. So the plane is where C and T are 0. So it's equal to the set of x, y, z, t belonging to the 3-sphere, on the squares equal 1, such that x squared plus y squared is equal to 1. And z and t are 0. Sorry, see what I'm saying. We're just going to have x and y. So that's a circle. X squared plus y squared equals 1, sitting inside of the 3-sphere. First 2 coordinates, circle. The other one, Q intersected with S3, is the second 2 coordinate circle. It's a set of 0, 0, d, t, such that c squared plus t squared is equal to 1. Those are 2 circles sitting inside the 3-sphere, described algebraically. And we just figured out that they must be linked, because you haven't quite visualized them yet, but they must be linked, because one of them bounds a disk in 4 space going this way, the interior part of that plane. The other one bounds the other interior part of the plane. The 2 planes intersect transversely in 1 point. So those 2 circles must be linked once. But you're still left with a visualization problem. You're thinking of 3 space as being the set of x, y, z, t, such that the length of it is equal to 1. And then you have specified a circle, and you specified another circle, and it's not so easy to see that one circle is actually diving through and coming around through the other one, right? That's not quite so easy to see. Or is it? Right? So now I leave it to you to think about, because I claim if you think about it further, you're going to be able to find a disk in the three-sphere such that one curve intersects the other curve in one point on that disk. So then you'd feel more three-dimensionally satisfied that it's your familiar length, okay? But this familiar length, the Hopf length, is actually consisting in two. You can start by saying I take two planes in 4 space that intersect in one point, the XY plane and the ZT plane, and then I restrict to the three-sphere and find the sort of outer boundary of that, and I get 2 circles, and those 2 circles are linked up with one another like this. So you can have some fun thinking about that. Okay, I'll leave it at that point. Otherwise, we go on all day with this one. Now, I had a number of other things to take up, but I wanted to make sure I did the new things that I wanted to do today before picking up on a number of threads from before. So here's one new thing that should be continuous for you with what we had said before. And that's the following, that we can talk about an oriented quantum. Now, and I'm going to perhaps use Q hat for it, all right? And let's look at it from the not theoretic point of view. Suppose that I'm thinking about oriented knots, and I still want to do this idea that we had before. Then I could have something like this, or I could have something like this. And the orientation would tend to give me something that looked a little different in each case. So what is it that's going to look different? Let's put it over here. I would have an oriented line in the knot, and I have another oriented line in the knot, and I would come up against another oriented line. And when I look at it with a different orientation, I might see a line going to the left or to the right as I approach an undercrossing line. So why don't I take that into account? Maybe I can get a stronger invariant. I can. So what I'm going to do is I'm going to say here I have A star B equals C. But here I'm going to say that I have A sharp B equals C, where star means I meet it to the right, and sharp means I meet it to the left. And I'll keep track of the difference between left and right. If I do that, then my Reidemeister moves and everything are going to look a little different. Here you had an A coming in, and A comes in here, and we're looking at what comes out here as A sharp. And here you have an A coming in and meeting itself to the right, so we have A star A. And of course, here we want this to turn into A, and here we want this to turn into A. So this is telling us that we want to have that A star A should be equal to A, and we want A sharp A equals A. No surprise there. It's just repeating what we needed twice, one for each of the operations, the left operation, right operation. So that's move number 1, no problem. What about move number 2? Well, in move number 2, it's more serious. I walk along and I see a B and it's going to the right, but then when I meet it again, it's going to the left, right? So I have A, then I have A star B, then I come out here and I have A star B sharp. And I want A star B sharp. So one operation inverts the other operation, and of course in the other order. So I really may need 2 operations, and I have to, and in my algebra, they may be constructed in such a way that they invert one another. But it's not that the operation inverts itself. There are going to be 2 operations, just like having an inverse matrix. good enough. Let's recall the basic formalism up here. So that I can use the board for the third randomized maneuver. So you see, this is easy enough idea, but it may lead to quite different algebra, and in fact, it does lead to some different algebra, and it leads to the Alexander polynomial, among other things, as we'll see in a moment. So let's see, we want the third move. No, I always want the most elegant third move that I can make. That. And of course, there are various orientation choices here. Let's have all the meetings be stars here so that we can see what will happen. Because what you're going to see is that let's just go through it. Going to see that the story is not different here. We can in fact write down basic requirement in such a way that it only involves one operation. So it's not going to get awfully more complicated. It's going to be all the difference is really going to be in number two. Watch what happens here. Suppose that this is A and this is B and this is C. Then I have A star B here, and then I have A star B star C. And you see, I don't have any mixture of operations to worry about. This comes out A star B star C, and this comes out B star C. And that's it. And if I go over here, then I have B star C here, and I have A star C there. Out here, I'm not. So just see, you got the product over here. Now, this is C, this is B star C coming down, and over here we have A star C times B star C. So we definitely need that each operation distributes over itself. And I will write and A sharp B sharp C is equal to A sharp C B sharp C. And then I'm going to assert that these are the column 1, 2, and 3 again. Are the axioms 1, 2, and 3 are the axioms for an oriented quantity. Now, you're a knot theorist, you're not an algebraist, perhaps, and you look at this and you think, well, you didn't illustrate everything. Maybe there's some more complication here as far as the knot theory is concerned. You could certainly define an algebra with these axioms, but is it good enough? What would happen, for example, if I switched this crossing and I wanted to get the identities that corresponded to that? Well, we could look, but in the interest of time, I'm going to let you look. We'll come back to it. I assert that you will find that any other identities where you seem to be mixing operations, change the orientation of one line, you'll have some mixed operations. It's all good enough. You can use these identities to get yourself through all the other problems that you can make up. Of course, you have to check it. So I leave it to you to check it, and it would be very interesting if I'm being too bold, and it turned out that you would give me an example where it didn't work, but I'm pretty sure that we've checked this carefully before. So we have this, this algebraic object with axioms that are almost as simple as the ones that I told you about before, okay? It's just that I have two operations, basically because I might meet the thing and then meet it going backwards, and I want those to cancel out. Now, do we have examples of this? Yes, we do. We have very interesting examples of this. So you understand I've done a little leap here, and you really ought to do some homework about this, but when we get back together on Friday, I'll do an example or two of rewrites that have to do with other kinds of drawings than these simplest drawings. You could start by maybe just reverse that line and then see what happens to the third Rademacher move, or switch this crossing and see what happens to the third Rademacher move, and see if you can get the identity that you find there to work on the basis of these alone, okay? So enjoy yourself with regard to that. I want to give you some examples of these kind of problems. So example number 1 is group theoretic. G is any group multiplicative. And I'm going to define A star B, B equal to B inverse AB, and A sharp B, B equal to B AB inverse, conjugation. Well, this actually is an algebra related to conjugation in a group. And these are inverse operations, obviously. So, so let's just check the axioms here. Maybe we should do it on the next board so we have more room.
Yeah.
Yeah.
I have a question. It's just a way
Oh, wait, maybe I should go back.
for the second rule, shouldn't it be like A star B is A and A sharp B is A?
And also the other way around. Is that what you were saying? We need both of them, of course.
Yeah, but what I meant, like, when you undo the time to write the last rules, like you should have A star B is A also, right?
I'm sorry, I'm not quite getting the question.
Can you
Sure.
What I mean
Be
is,
my guest.
sorry. Thank you. Like when you undo it does right? Like you undo this, and you have just this B.
Yeah.
All of this should be A, right?
Right.
And
right.
but would that imply that A star B is A also?
Oh, no. You're comparing the two pictures. And in this picture, you have an A, and in this picture, you have a B. Okay, that's fine. And in this picture, this appears in that picture. It's in this picture, but it's not in this picture.
Okay.
Now, I know what you're thinking, and it's a point that we ought to understand, that when we do a move, we're talking about the before move and the before shot of the move and the after shot of the move. But in the world of continuity, you think of the move as happening like my rope slides slowly through, and then in doing a move like a Rademacher 2 move, in continuity, it looks like this. This gets a little smaller. At a certain point, one of these is just punching underneath the other one, and then they're apart. And this is a critical point. I mean that in both a technical sense and a non-technical sense. It's a critical point in the sense that it's the critical place where in the continuous sequence of images that constitute what we're thinking of as the move, there is a point which goes outside the category of diagrams that we're allowing ourselves, right? We're only allowing ourselves diagrams where the curves intersect each other transversely, different pointing tangent vectors. But at that point, the tangent vectors are coincident, right? So for every one of these moves, there's a critical point. And the move is designed to show you how to get from before a critical point to after a critical point. And it doesn't talk about the critical point, and it's really an algebraic entity. The curve is a kind of algebraic or discrete, I'm sorry, the curve. The move is an algebraic or discrete step. It says you can take this thing and you're going to replace it with that thing. But underneath that is our intuition about the continuity. And that intuition is very important because it's actually one of the sources of how we get the moves. If you thought, sorry, I'm digressing, but I wanted to say this at some point. If you thought to yourself, well, I want to have topological moves on these diagrams for the knots. But I know that when I do some things, I get these critical points. So if I found out all the critical points that are involved in the things that I want to do, then for every type of critical point that I encounter, I probably have to write down a move. Oh, that's a way to create moves. So now you see, think about it. Let me do it over here or on the next board. Yeah. So we're talking about moves and critical points. So you're thinking of moving things around in the plane, never mind over and under crossings for the moment. Let's just try to think of it this way. And then you say, let me see, if I go from here and let that become smaller and go away, then I would have a critical point somewhere in here where these tangent vectors were the same, but then I want to think about as corresponding to this curve. And so I need to go across a certain kind of critical point there. I'm going to need a move in order to do that. Because if I ever want to get from A to B, and there's no way to get from A to B, except by going out of the category, then I'm going to have to put in a move in order to, or a rule in order to do it. So it's almost philosophical. You're in some category, but within that category, you wish to get from certain configurations to other configurations, but there's no way in this category to get there. It's geometrical, so you can see how to identify what it is, what critical thing it is that you need to do to go, and then you say, I'll just go out of category and I'll tell you that this is the move. I go from here to here. So this is one, and this is another, where this would become a tangency in the middle, and then it would come apart. And in the case of the third Renemeister move, the middle position is where all three lines are touching one another. And then on the other side of that, you have this. So then you say to yourself, well, what kind of critical points can I have for curves? These are the moves that I want, but have I got everything? What kind of curve touchings are bad, right? And you realize, oh, one kind of bad curve touching is three curves going through a point because I'm only allowing two to go through a point. So this is bad. Tangency between curves is bad. And losing tangency to have the same tangent point, that's bad. And then you start to think, well, are there any other critical points that occur for curves in a plane? And you realize But that's it. That's all there is. And that's why there are 3 Reidemeister. That, of course, is not the complete proof of the Reidemeister moves, but on the other hand, it's a way to generate moves. If you went up a dimension and started thinking, as I've indicated, that you might, about surfaces in 4 space and how they would move around, then the kind of critical points that can happen for surfaces in 4 space is more complicated. So if you then proceed to think carefully about all the critical points that can happen for the way surfaces behave in 4 space, you actually arrive at what correspond to the Reidemeister moves up there in 4 space. And it can be done in higher space as well, but gets even more complicated because the kind of critical behaviors get more complicated. And in general, what we're looking at is you're in a certain category, but you need to leap out of that category into some larger category in order to make the sense out of what you're doing. So it keeps coming up again and again at that structural and philosophical level. Okay, so I was about to do an algebra exercise. We were going to define A star B to be equal to B inverse AB, and A sharp B to be equal to BA B inverse. And now we want to see that that gives us an oriented quantal structure on a group. And this is an easy exercise. Let's just do it. A star A, well, that's A inverse A, which is certainly A, and A sharp A equal to A inverse, which is certainly A. So that's good. What about A star B sharp B? Well, you see, we're going to have B times B inverse A B inverse, right? Sharping with B does B inverse on the outside, and starring with B does B inverse AB, but groups are associative, so this is B inverse A, B inverse, and that's equal to A. So it works. And what about the self-distributivity? A star B star C is equal to C inverse B inverse A B C. And A star C star B star C is equal to, now let's see, it's equal to B star C inverse A star C B star C. And then I have to put those in. And this is equal to B inverse C B inverse. And then C inverse A C. And then C inverse B C. And then that's the inverse. And the inverse of a product in a group is the reverse product of the inverse. So the inverse B. Somebody made a mistake. Yes, here. The inverse piece. Right? C inverse BC, the inverse AC, C inverse BC. This inverse that, right? So now inverse. So that's C inverse B inverse C, C inverse A, C inverse B, C. Groups are associative. These cancel, and I get C inverse B inverse A, B, C. C inverse B inverse A, B, C. So that's correct. So it self-distributes, and of course you can check the other one just as easily. So given any group, the operation of taking conjugates gives us an oriented model. And these are obviously in general very different operations, right? So we have non-trivial examples of oriented quantals. Now I give you another example. We'll come back to that because this is actually related to what people call the fundamental group of the knot. This example two. Let M be a module over the ring Z of T the inverse. This is Laurent polynomials in T. For example, T plus 3T inverse plus T to the 7th plus 99 T to the minus 1000. Okay. Just polynomials with negative and positive exponents, coefficients in the integers like that, okay? That's a nice ring. And M is a module over the ring. If you're maybe feeling rusty about your modern algebra and you're wondering what's a module, well, a module is just like a vector space. It means that elements of this can multiply elements of this. So you can, so these are the scalars. And these are the vectors. M is an additive abelian group. You can add them, just like vectors. You can add vectors. You can multiply a vector by a scalar, and you're used to that, right? So I don't want to write down the legal definitions of everything at this point. But when you have a scalar, you think of it as a number, and you can multiply a number times a vector, right? You can scale a number by a vector. Here, you can scale a modular element by multiplying it by a polynomial, but it's analogous to multiplying it by a number, okay? That's what I have. And then I'm going to define A star B to be equal to TA plus 1 minus T times B. And this is like multiplying this by a number and that by a number, and the A and B are elements in the module. And the A sharp B is equal to T inverse A plus 1 minus T inverse times B. And those are my rules for forming an oriented quantum. Now, you could have gotten, you can get to this, you could find this, find these rules by trying A star B equals RA plus SB, and A sharp B is equal to BA plus QB, where R, S, P, and Q are supposed to be somebody in the scalars, right? And then you try out the rules of the quandle and see what it forces you to do, okay? And then you would find that this is the most interesting solution to what's forced by that. So that's an exercise if you wanted to try it out. But let's just see that this works. For example, A star A. A star A is TA plus 1 minus TA. And as I said, modules are just like multiply a number times a vector. So you can multiply a number times a vector and another number times a vector, and that's equal to the sum of those two numbers multiplying the vectors. Scale module rules are the same, and this is 1 times A, and on the scalar times a vector is equal to the vector. So see, you're just behaving like as though we're vectors, but it's more general than vectors. You're running those scalars out of a different ring. And similarly, A sharp A is equal to A. And what they do invert one another, let's try that. A sharp B sharp the star, I'm sorry. A star B sharp B. Okay. So according to us, this is equal to T inverse B plus 1 minus T inverse multiplied by A star B, which is TA plus 1 minus T times B. Huh? You have to multiply that all out. Okay, so I get T inverse B plus T minus 1 times A, multiplying that out, plus 1 minus, I have to multiply 1 minus T inverse times 1 minus T. So that's going to be 1 minus T inverse plus 1. Going to be 2 minus T inverse. So plus 2 minus T inverse applied to B. So let's see here. I make some mistake. T inverse B plus 1 minus T inverse times. Yeah, of course, I made a silly mistake. We'll start all over. Right, for wasting time. So it's T inverse times the first one, A star B, plus 1 minus T inverse times the second one, right? That's my rule. Now you're memorizing my rule, probably, right? I mean, I set it up so it would be easy to remember. You multiply the first one by T and the second one by 1 minus T, or inverse, as the case may be. It's good to remember. Now, this is equal to T inverse times TA plus 1 minus T B plus 1 minus T inverse applied to B, and that's equal to A, there's an A, plus T inverse minus 1 times B plus 1 minus inverse times B, and that's equal to A as desired, and the other way will go the same way, okay? So it's working, and I leave it to you to check self-distributor. It's not hard either, that this works. Now, this one is kind of calculable, so let's try it out on a knot and see what happens. Here's a trephone knot. Orient. So, in this case, all the operations will be stars. Maybe I'll start out by calling this X. I don't know what it is. And I'll call this one Y. And then we're going to walk along the knot and see what the other guys will be labeled. So this will be X star Y. Okay. And then X star Y is going to meet X. So we're going to get X star Y star X by the time we get to here. But that had better be equal to Y. So we get an equation. So this is the analog of what happened with the numbers. With the numbers, we said 0, 1, 2, 3. 3 must equal 0. That's what happened with the numbers. Now it's going to happen at the algebra level, the same thing. A relation is going to occur. And what relation will this be? Let's see. So we're going to start with the relation and write it out in the quantile. So we have x star y star x equals y, a kind of algebraic version of the knot. And this says that t times x star y plus 1 minus t times x should be equal to y. And that says that t times tx plus 1 minus t times y plus 1 minus t times x is equal to y, which says that t squared x plus t minus t squared times y plus 1 minus t times x minus y equals 0. So let's see, I should collect my terms as best I can. I get t squared minus t plus 1 multiplied by x minus t squared minus t plus 1 multiplied by y is equal to 0. Or t squared minus t plus 1 applied to x minus y is equal to 0. And you see, this is the analog of the modulus for box coloring, the coloring, the 2b minus a coloring that we were doing before. It's the analog of the modulus. It's a scalar. It's like a number, but it's now up leveled. It's a polynomial, it's a Laurent polynomial, and this Laurent polynomial is going to have to kill off anybody in the module, right? So that means that we must work. This implies that we should work in T inverse modulo setting this polynomial equal to, just like the integers mod 3, only it's the Laurent polynomials modulo that polynomial. And this polynomial, delta k of t equal to t squared minus t plus 1 is the Alexander polynomial of the knot. And it is the analog of the determinant of the knot that we've seen before, being the number which we need to kill off all the to be in that particular value of modular arithmetic. So what we're saying is that we can label the knot, we can color it, but we're coloring it from elements of the module, and we can color it consistently from elements in the module if we work over the ring Z mod the polynomial, and the polynomial ends up being well defined up to A equal dot B, which means A equals plus or minus T to the n B for that some integer. Because multiplying this by t, say you get t cubed minus t squared plus t, it'll still be the same. It will do the same job. It will kill off everybody if the original one did. That's a unit in the ring. So that's Alexander polynomial from this point of view. Alexander polynomial can be thought of as coming from the Alexander quantum. Of course, Alexander didn't know about quantums, but he had a structure that's similar to that. And the Alexander quantum is the one I just told you about. A star B is TA plus 1 minus T B and A sharp B, the inverse A plus 1 minus the inverse B. There are many ways to think about the Alexander polynomial, of which this is only one, but this is a good one for doing some experiments. You see, if you want to, you could write down the entire system of equations and go through what we did before over the integers, basically, and get a determinant that would give you the Alexander polynomial. In the interest of time, I won't do that today. But on the other hand, you can try it out by propagating the set of relations. And for small knots, if you start with variables here and propagate the set of relations, then you will, if you could only start with 2 variables here, then you will get exactly this for small knots. You will get some polynomial multiplying the difference between the 2 starting values, and that polynomial will be the Alexander polynomial of the knot. Some of you may have seen Alexander polynomial before. Maybe you've seen it this way, but there are quite a number of different definitions of the same polynomial that Alexander found. And Alexander's original definition is not this one. This is a nice combinatorial way of thinking about it that happened later. You will notice, let's write that quantal definition again. A star B is TA plus 1 minus T B, and A sharp B is equal to T inverse A plus 1 minus T inverse B. Note the following. And if we take T equal to -1, then what will these operations be? Minus A, 2. Minus A, 2. So this is box coloring. And the determinant of A, of K, as we have defined it, is equal to the absolute value of the Alexander polynomial evaluated at -1. If you let T be -1, then this whole calculation becomes the one we had before. And it does, right? Look at that. If you put T equal to -1, you get 3. 3 being the modulus. So that's what happens. That we really have, doing it this way, we really have generalized our Fox coloring situation, our unoriented quantal situation into an oriented situation. But in so doing, we have created a much richer structure. We associate to every knot a polynomial, the Alexander polynomial, and up to equals dot, you can prove that if 2 knots are equivalent, then they have the same Alexander polynomial. So Alexander invented his polynomial around 1928. And I will tell you his definition for fun, but this is the one that comes out most naturally from the line we've been following. And you can try this out. I suggest the following exercise. Find the Alexander polynomial for the figure 8 number. Right? So you can try the same yoga, the whole thing. Propagate, label 2 lines X and Y, propagate around, get the relation that you need, and then write out the algebra of the relation, factor it out. You won't have to use any matrices, but you will get a polynomial multiplying X minus Y, and that will be the Alexander polynomial with figure 8 knot. It should specialize to 5 when you take t equal to -1, because it's generalizing what we did before. And for some small knots, you can calculate Alexander polynomials this way quite quickly by just looking at those relations. Okay, so I'm still not done with new material, so it looks like our loose threads are going to go off. Most of them are going to go off into next time, but let's continue here. I can define the group of the knot. I'm going to call it G of K, but it's actually equal to what's called pi 1 of K, but we'll have to explain that in a moment. This is the group of the knot. And I'm going to define it the following way. We're going to use the group quantity. So now we're going to have A and B and C will be equal to B inverse AB. And the other way around, A and B, and then C will be equal to BA, B inverse. It's possible I will want to revise this after I tell you something and reverse the definition to BA, B inverse there. I always forget, but we can take it this way for the time being. This means that we have one relation at each crossing. We form the group equal to a set of generators and a set of relations where the generators are in one-to-one correspondence with the arcs in the diagram, and the relations are in one-to-one correspondence with the crossing relation. So you see how that's going to go? Let's do it for a triathlon. I'm going to have labels for the arcs. These labels are elements of a group. Not the quandle, but we're really using the quandle in the background to motivate it because the quandle operation is B inverse AB if you use the group. And then the group of the trefoil knot is going to be the group that's generated by A, B, and C. And then the relations are, well, let's see. From crossing number 1, I'll get a relation. From crossing number 2, I'll get a relation. From crossing number 3. From crossing number 1, I get that C is equal to A inverse BA. right? This is the operand one, and that's the one that came in. From crossing number 2, I got that B is equal to C inverse AC. And from crossing number 3, I get that A is equal to B inverse CB. All right. So then the group is C A equals B inverse CB, B equals C inverse AC, and C is equal to A inverse BA. And we get a group defined by generators and relations. In my rush to tell you things before about quandles, I forgot to tell you that I could define a quandle associated with a knot or a link in the same kind of way. Namely, the quandle would be generated by the arcs in the diagram, modulo the quandle relations, and then the resulting algebraic structure would be a quandle. But let's talk about groups. You may not have thought of either of these constructions before. This is one of the intellectually simplest ways to make a group. I say, I tell you what the generators of the group are, and I tell you what the basic relations are in the group. And then what this means is that you write down all possible group expressions. You can write down things like, you could write down something like, for example, A inverse B, A, C, D, D, A, B, A. You just write down all possible finite words that you could. And if you have a finite word like that, somebody that's written out in terms of the generators, and you have another one, you can put one next to the other and you get a longer word. So you can multiply. So that's how you multiply. And of course, things have inverses because the inverses are there. And you always have that if you put an A next to an A inverse, you will get 1, the empty word. And so when you take all possible words and you multiply them together in this way, you get a group. And then if you don't put in any relations, then all you have is what the words generate. That's called the free group. And if you have some special relations like these, you have to apply them. So for example, this word here is equal to, well, A inverse BA is equal to C. So this is C. And then we have C. And then we have ABA. Sorry. And so we got C squared ABA, a simpler word out of the more complicated word. So if you think about it a bit, then you look at all possible words, modulo the equivalence relation that's generated by these individual relations. Then you get a group. And that's called the group described by these generators and relations. How many of you have seen this before somewhere? Could be nobody or maybe 1 or 2. Because that's what I kind of expected, because most people, when they study even a modern algebra course, they don't necessarily contact this fundamental idea. But it's used all the time in topology and also in certain aspects of group theory. For an exercise so this defines a group that's associated with the knot. And this group has a geometric interpretation along with being related to the quandle. And I wanted to explain to you in the last few minutes of today what the geometric interpretation of this is. But before that, here's an exercise for you. Consider the following group, H. This group is generated by sigma tau such that sigma tau sigma is equal to tau sigma tau, and sigma squared is equal to the identity, and tau squared is equal to the identity. So that H has 6 elements, and that H is equivalent to permutations of 3 things. The group of permutations of 3 things is one of the simpler groups, right? It's a first non-commutative group. You have 3 things, and you have the operations of permuting them, which are functions from 3 things to 3 things. So diagrammatically, what I'm saying is that you could think of sigma as corresponding to interchange 2 things out of 3, and tau as corresponding to interchanging the other 2 things. And then you'll see the patterns fit. You'll see that if you compose these permutations, for example, sigma, tau, sigma, if we compose permutations, you interchange the first 2, then you interchange the second 2, and then you interchange the first 2. So the first one ends up in the second place, and then after the next composition, it ends up in the third place, and then it's left alone. 1 goes to 3, but 2 goes to 1, and then it goes to, it's 1, and then it goes to 2. Follow that down, and this one goes here. But if you look at tau, sigma tau, then it's tau, sigma tau, like this, and the first goes to the third, and the second goes to the second, and the third goes to the first. But that's the same as this. These are exactly the same. They're just different diagrams for the same permutation. The permutation is 1 to 3, 2 to 2, 3 to 1, 1 to 3, 2 to 2, 3 to 1. 1 is obtained by interchanging the second 2, then the first 2, then the second 2. First is obtained by interchanging the first 2, the second 2, and the first 2. This is the actual group, a very concrete group that has these relations. But here I've said, let's just consider a group. Oh, and the square of any of these are equal to the identity, because if you took sigma and you squared it, this would be our diagram for sigma squared. Because see, 1 goes to 1 and 2 goes to 2. So as a permutation, it's the identity. So this is a concrete view of the group I have in mind, the symmetric group on 3 letters, the group of permutations of 3 things. But over here, I've only told you the rules for the group, nothing more. But if you play around with those rules, you'll find out that every word you write can be reduced to 1 of 6. There are only 6 possibilities, the elements of the group. So play with it and you'll see. And if you play with that, that's a good exercise. If you play with that exercise, you begin to understand what happens here. Another exercise, which I'll do next time, is that this group is isomorphic to, by playing with its words, what's generated by just A and B, but ABA equals BAB. It looks very similar to this group, but it's bigger. The elements don't square to the identity. So this comes from doing a bit of algebra with this. We can get to that. So this is the group of the knot, and it's a very fundamental one that's related to the general quantum. But now the geometric interpretation, and we'll stop for today. suppose that I put a loop around. I could say this more generally, but I'm going to say it in the context of the knots. I have a special point here, and I consider a curve in space that goes around the knot and comes back to my special point. Okay? That. So this is an arc of the knot. And this is a loop at the base point star. And I'm going to tell you that I define I1 of K, our knotted length, to be equal to the loops at the base point modulo homotopy. Homotopy means deformation of loops. We'll say this more carefully. Definitely, when we have more time. Deformation of loops, strictly continuous. Right? Just continuous deformations of loops. A loop can go through itself if it wants to. It can go through another loop in time. You're just going to see a loop moving along in time. But these loops, the loops, are all in R3, if the knot is in R3, minus the knot. All in R3 minus the knot. A loop can be deformed in time any way you like continuously. It has to stay at the base point. It begins at the base point, comes around, but it can do whatever it likes otherwise. But it can't go through the knot. So we're going to measure the knot by looking at all possible loops that go around the knot in the complement of the knot. Okay? That's a beautiful idea that goes all the way back to Poincaré in the 1800s. And if you have two loops, you multiply loops by do alpha, then do beta. So for example, if I had another curve over here, add another arc. Let's call this one A, corresponding to arc A, and we'll call this one B. And now we would go from the base point and around this one and come back. Of course, you could go around any number of times, but I'm just going around once, right? So I go around the other arc of the knot, which is somewhere over there. And then to do them together, let's say I wanted to do B first and then A. So then I would go along B. Sorry, that went backward. Going along B, I go back to base point, then I go along A, and that's BA. Do this, and then do that, all right? But this is to be deformed, in this case, to C, which I'm about to draw by erasure, where I'm allowed to deform it a little bit in the middle. The endpoint has to stay and everything begins and ends. Loops begin and end at star. Loops always begin and n at the base point, right? So if you're deforming it, you can't deform the beginning. The beginning starts at the base point, but somewhere in the middle, which is what happened here, I did B. Then I decided I would change it just a little bit in the middle so that it didn't hit the base point. And then it would go around the other one like that. So I could do that, and then I get one single loop, where you see clearly one single loop. That is the result of multiplying B and A. Pictorially a single loop. Now maybe this one went under that one, but that's the story of multiplying the loops. And this forms a group. And the key thing to seeing that it forms a group is to see inverses. How could you get an inverse to a loop that went around an arc? Well, let's see. Here's my base point, and I go around, and then I decide to go backwards, same direction that I went, and come back to base point. Now, what I just drew is certainly equivalent to just doing basically nothing, and here's the arc. Right? So that looks like I did an inverse, and I did. The inverse loop is the loop that starts at the base point and runs in the opposite direction and comes back to base point. So you do this, so to get the inverse of a given loop, you go out and around and come back to base point, and then you go right back along the same loop and come back to where you started, reverse time on the loop. And then in the middle, you can deform it a little bit, and then you start deforming this in the middle, and it becomes more and more small and simple. And of course, the identity is do nothing. Doing nothing is a perfectly good loop. The value of the loop is always the base point. You never left the base point throughout the whole time of the passage, say from the interval along the interval 0, 1, you have time, and all that time you just stay at base point. So that's the fundamental group of the knot. And now what I'm claiming is that the group of the knot that I described to you today is isomorphic fundamental. And the basic point about that is as follows. If you have two parallel lines and you run a loop around two of them, you have to understand what element in the group that's going to be. You need to see this. So let's call this G, right? I wrap around the two lines and come back to base point. Well, I claim that it's B times A, and that we were already looking at it. And sorry that I'm taking up your time, but let's draw this picture. I'm going to draw G. And you remember, when I'm in the middle, I don't actually have to go all the way back to base point. I could just come near the base point. And then I'm going to go around to A, and then I'm going to come back to base point. There we go. A, this is B. And what I've drawn here is B times A. O star isn't the quantum operation anymore. I'm just going to write B times A. I wasn't calling that. It's just BA. Right? Now, I hope that picture is clear to you because that's sort of the key to the whole thing. If you have a couple of lines in the knot and you have a group element, which is obtained by using right-hand rule to go around one line once, then if you do B, and then you do A, you see that this deforms, just slide that back in between the two lines, and it's the element G that's going around both of them. Okay? With that in mind, consider a crossing. I'd like to draw it this way. Okay. Everybody's oriented on them. And I can draw a loop that goes around both of these down at the bottom, like that. And this is, well, let this be A, let this be B, and let this be C. All right? So this loop down here is A times B, right? By what I just said, A times B, from right to left, is the product of a circling loop. But this loop is deformable all the way up to the top. And up on the top, you would have BC. So it says that at every crossing in the fundamental group, you're going to have a relation, and the relation is that A times B is B times C. A times B is equal to B times C is the same as C is equal to B inverse AB. And that's the relation that we used to define G of K. So the relations in the fundamental group are coincident with the basic relations by which we define G of K, which came from the quantum. And of course, it requires more work to show that the fundamental group is in fact exactly the group that's generated by the arcs and one relation for each crossing. I'm not going to prove that here, but I'll give you a reference for that if you're interested in finding it. But that's the core of why it is that the fundamental group of the knot is equal to the formally defined group that we discussed in relation to the quantum. And now we've, in our way, reconstructed knot theory up to about 1930 and beyond, because the points of view I'm using are beyond. But the fundamental group was, in fact, one of the first things that people started thinking about in relation to knot theory. And that had to do with the history of the world. Poincaré had invented the fundamental group for a general topological space. And topologists got the idea, oh, maybe we could study these knots that Lord Kelvin thought were atoms in the luminiferous ether by using the fundamental group. And there was lots of motivation for thinking about it. And so the ether disappeared, but by around 1905, Max Dane had used the fundamental group to show that the trefoil knot and its mirror image were different, and the subject had begun. So I'll stop here. Thank you.